In this lecture, I'm going to state the LGV lemma. So what is the setup for the LGV lemma? You're given S a set of vertices or nodes. You're given a function V from S cross S to the real numbers, though in general you can take it to any ring, any commutative ring, and we call this the weight function. And you're given points A1, A2, AN in S, and another set of points B1, B2, Bn also in S. So the way you should visualize this is that you have points A1, A2, AN and B1, B2, Bn, which are part of some network of nodes. So you could think of these as input nodes and output nodes in some, for example, some machine learning network. And this network has connections. Something like this. Now, a path in S. So this S consists of all the nodes, including the nodes A1, A2, AN and the nodes B1, B2, Bn. A path in S will be denoted by the Greek letter omega from X to Y. So we'll call this omega is a path from X to Y. Is just a sequence of nodes S0, S1, Sn in S, such that S0 is X and S1 is Y. So in this diagram here, you can see a path from A2 to B1 with, well, this is from A2 to B2, and this path has 0, 1, 2, 3. So it has S0, S1, S2, S3. So that's a path from A2 to B2 in this network. And given a path W, the weight of a path is defined as of the path omega with vertices S0, S1, Sn is defined to be weight of omega is product I goes from 1 to n weight of Si minus 1 Si. Now the matrix that the LGV lemma will address is the following matrix. M equals Mij, I goes from 1 to n, j goes from 1 to n, and it's given by Mij equals is the sum over all paths omega from Ai to Bj of the weight of the path omega. And the LGV lemma is going to tell us about the determinant of such a matrix M. Let us look at some examples of such matrices. So let's consider the array S an array of nodes S, you just think of it as n cross n. So think of n as non-negative integers. So n cross n is the Cartesian square of non-negative integers. However, we are going to plot them in sort of matrix notation where I comma j denotes the node in the ith row and jth column of the array. And we'll define weights as follows. We'll define weight of the node I comma j to I comma j plus 1 to be 1. We'll define weight of I comma j to I minus 1 comma j to be 1, and we'll take all other weights to be 0. In effect, what this allows is that you have I comma j, a node. You can go from there with non-zero weight either down one step, no, I comma j plus 1, so that's to the right by one step, or you can go down one step, up one step to let's see, I don't have enough space here. You can go up one step to I minus 1 comma j. And since the matrix only considers paths of non-zero weight, we don't effectively, what we're saying is that we're going to be looking at paths which at each step either go one dot to the right or one dot above. Okay, so let me ask, what is the number of paths from, let's say, this node here, 3 comma 0 to let's say 0 comma 4. So question is, what is sum omega from 3 comma 0 to 0 comma 4 of weight of omega? So to go from 3 comma 0 to 0 comma 4, and we are only allowed to use steps towards the right or steps towards the top. So we can go maybe like this. If you want to think of this as a path, you can draw arrows. So here is a path from 3 comma 0 to 0 comma 4, and its weight is 1. So each valid path here, each path with non-zero weight has weight exactly 1. So we're just counting the number of ways of going from 3 comma 0 to 0 comma 4, always taking steps to the right or above by 1 unit. Now, all in all, there are 1, 2, 3, 4, 5, 6, 7, 3 plus 4 steps to be taken. And out of those 7 steps, exactly 3 have to be rightward steps and 4 have to be upward steps. So the total number of paths is just 7 choose 3, or you can think of it as 3 plus 4 choose 3. So now we can realize the matrix that we saw in the last lecture, the one that comes from Suchi Prastara, its minors we can think of as matrices that are described by this setup for the LGV lemma. So for example, if we take the matrix Mij given by ijth entry is alpha I plus beta j, choose alpha I. Let's just say this, say for some alpha 1 less than alpha n, beta 1 less than beta n. This n by n matrix is a submatrix of the Suchi Prastara. It's the matrix whose determinant is alpha 1, alpha n, beta 1, beta n, where aij is I plus j, choose I. So of course, so maybe I should write determinant of M. Is this minor of the Suchi Prastara. Let's look at another example, and this one is related to, it's got the same S, but this one is going to be related to the Meru Prastara. So S is as before, S and B as before, which means that again you're allowed steps to the right or steps going upward by 1 unit. But we are going to define the points between which we draw paths differently. So we are going to take the points a comma 0 and b comma b. So the number of paths, say how many paths are there from 5 comma 0 to let's say 2 comma 2. Number of paths from 5 comma 0 to 2 comma 2. So totally how many steps do you have to take? So you have to take 5 minus, so to go from, so you have to take 2 steps to the right and you have to take 5 minus 2 steps to the top. So totally you have to take 5 steps, of which 2 have to be to the right. So this is going to be 5, choose 2. In general, the number of steps from, number of paths from a comma 0 to b comma b is a choose b, which is positive if and only if a is greater than or equal to b. So this is so if we take taking ai to be alpha I comma 0 and bj to be beta j comma beta j, we get determinant of M equals determinant mij. This is just the minor associated to the Meru Prastara. An example of a path from 5 comma 0 to 2 comma 2 would be something like this. And you can check that there will be exactly 5 into 4 divided by 2, 10 paths from 5 comma 0 to 2 comma 2. Now, an important hypothesis for the LGV lemma to hold is what is known as the crossing condition. So let me explain now what the crossing condition is. The crossing condition says the following. Suppose we are given S, V, A1, A2, AN, B1, B2, Bn as above. That is, S is some array of nodes, B is a weight function, A1, A2, AN, B1, B2, Bn are some sets of n points in the array. The crossing condition states that so let me just change colors here. For all I less than j between 1 and n, and all I prime less than j prime between 1 and n, and paths omega from ai to bj and eta from ai to bj prime and aj to bi prime. So let me just draw a picture for you. So we have these nodes a1, a2, and then we have ai, and then we have nodes b1, b2, bi, let's say bi prime, and then you go down to aj, and then all the way down to an, and you have bi, then you go down to bj prime, and then all the way down to bn. So you have ai, aj, bi prime, bj. Now omega is a path from ai to bj prime. So it starts here and it may go up and down a bit, but it ends up at bj prime. And eta is another path, and this path is from aj to bi prime. Now the important point here is that omega goes from ai to bj prime, j prime is greater than I prime, and eta goes from aj to bi prime. So these paths omega and eta, their initial points are I and j. I is less than j. Their end points are j prime and I prime respectively. J prime is greater than I prime. So these paths are somehow in inversion. And the crossing condition, which is very clear from this picture, says that there is some point here where they will cross. So it says that, so if omega is the path S0, S1 up to Sk, eta is the path T0, T1 up to TL, then there exists an integer m between maybe I'll just write 0 and k, and an integer r between 0 and l, such that Sm is equal to Tr. Let's call this point P. So here's the point P in this picture. It is a point which is on the path omega as well as on the path eta. So what you're saying is that if two paths their endpoints are in inverted order from their starting points, then these paths must cross somewhere. Now this is completely clear when your network of nodes that you're looking at is something like this, where you have a network of nodes in the plane, and the points a1, a2, an, b1, b2, bn are in order with respect to each other. So if you have a network which looks like this picture over here, the crossing condition will definitely hold. However, the hypothesis is a little more abstract. You don't need to necessarily be able to draw the network, you just need to prove the crossing condition. But in the application that we will see, it will always be visual. We will draw a network to construct our matrix. So that's the crossing condition. So it says that if you have a pair of paths, the path omega starts at ai and ends at bj prime, the path eta starts at aj and ends at bi prime, I is less than j, I prime is less than j prime, then these paths must cross somewhere. Now we are ready to state the LGV lemma. Let S V A1 AN B1 Bn be as above, and assume that they satisfy the crossing condition. Let M be the matrix Mij, where Mij, this is an n by n matrix, where Mij is the sum over all paths omega from ai to bj of the weight of omega. Then the LGV lemma says that the determinant of M is equal to the sum over all configurations omega bar of n tuples of paths, where omega I is a path from ai to bi, and these paths omega 1 up to omega n are pairwise non-crossing. So this means that omega I and omega j can have no points in common if I is not equal to j of product I goes from 1 to n weight of omega I. Now the left hand side of this identity is a determinant. It's an alternating sum of weights of paths. The right hand side is just a sum of weights of paths. So right away we get a nice corollary. There are no signs on the right hand side. So we can say that if V takes non-negative values, then we know that the determinant of M takes non-negative values, and moreover, if there exists pairwise non-crossing paths, omega 1 omega n with positive weights, with non-zero weights. In these calculations, we only worry about paths with non-zero weights. The remaining paths, they may as well not exist with non-zero weights, such that omega I goes from ai to bi. Then we can conclude that determinant of M is actually strictly positive. So using this, we can show that if we start with the array of the Suchi Prastara, then you can show that there always exists non-crossing paths. So alpha 1 alpha n, beta 1 beta n is positive for all alpha 1 alpha n, beta 1 beta n. And you can also show that for the Meru Prastara, this is positive, well, this is non-negative for all these alpha 1, alpha n, but you can also say when it is positive. If and only if alpha I is greater than beta I, greater than or equal to beta I for all I goes from 1 to n.